All right, guys, we're going to continue on with day one. We're going to do section 1.2, computing limits. And basically, the first part of this section has to do with just computing limits algebraically. And so the first thing that you should try for basically every limit is doing substitution. Substitution is the most important one because it's the easiest thing to do. And so if you look at example number 1 here, you can see that the limit is x approaches 6 of this polynomial. You literally have to plug in 6, because remember we talked about in the first section that what is a limit as x approaches some constant? It's going to be the corresponding y value. So this would be a 6. The corresponding y value of the function. Like, where are we all leading towards? So if we go look at this function right here, and we have some crazy thing like this, and I want to know what's the limit right here at this value. We call this a. Well, that limit is going to be equal to whatever this corresponding value is for the function with respect to y. So with that being said, we can define this limit by just direct substitution by plugging in. I mean, that's really all we're doing. We are literally substituting in by plugging in. So this question right here, I think the answer is 87. You're not expected to do this example actually in your head. I would imagine that they would have you do this. So if this would be like a multiple choice question, then this number would be much nicer to solve. I will tell you that in BC Calculus and even in AB Calc, you won't see something as basic as substitution, but it does give you a good foundation for what you should do for limits, or at least the idea of what a limit is. And then in example number 2, you do the exact same thing. So we have a limit as x approaches 5 of the cube root of 4x plus 44 over 6x minus 29. So just like in the previous example, we're going to take this function and we're just going to plug in 5. So 5 times 4 is 20. And then we're going to leave 44 alone. Everywhere you see an x, you're going to plug in. So 6 times 5 is 30. And then 30 minus 29. And this is one of those problems where this is actually pretty easy to do without a calculator in your head, because obviously 20 plus 44 is 64. 30 minus 29 is 1. And so the cube root of 64 is going to be equal to 4. So this limit right here is 4. So again, if we were to take this function right here, and we were to put it on a graphing calculator, and we were to graph it, and we would look at, okay, when we go where x equals 5, where would this be on the y? And it would be at 5, 4. So this would be the solution to this function at x equals 5. It'd be 5, 4. So that's really what a limit is in a very easy journal fashion. In the next example, we get a little bit more complicated, but just like I said, a little bit more complicated. If you plug in 1 to the top, you're going to get 0. And if you plug 1 into the bottom, you're also going to get 0. So this is going to be a 0 over 0. What we call this is an indeterminate limit. And so what we need to do here is, first of all, we never, ever say it's equal to 0 over 0. We cannot do that. So we want to just make sure, I've just put this as my little side piece, but you do not want to say that it's equal to 0 over 0. And then what we do is we want to be able to simplify this in some fashion so that when we plug in x equals 1 to our function, or our revised function, I should say, then we're able to get an actual value that's not 0 over 0. Okay, just really quickly, if this had been 0 over a number, then the answer would be 0, right? 0 divided by some number is just 0. If this had been some number over 0, then it would be undefined. All right, so let's look at this. So what I want to just say really quickly about this is that I'm going to go ahead and I'm going to keep my notation. And that's really important in calculus. You got to keep on saying the notation. If you drop the limit and you just start worrying about this function, x can be anything. We're looking at where x is approaching 1. If x had been approaching 2, then we would actually have just did substitution and got a value for that, and we'd be good. So we really want to make sure we keep the limit here. Why didn't I keep the limits over here? Well, because I was just going ahead and substituting in numbers. Notice that everything that I wrote down here and here were numerical values. Here I'm still dealing with variables here. So I'm going to go ahead and write down, there's nothing I can do in the denominator, right? And so obviously I hope that it should be pretty obvious to you guys that now we're going to do our factoring part, right? So this is a way to simplify this guy right here, is to factor it. And one of the things that I always tell students is, if it ends up being 0 over 0, the most likely 99.9% of the time, this x minus 1 down here is going to be a factor up here because you want to be able to cancel something out. And if you look at this, this actually ends up being x minus 1 times x minus 5. So this is the factored form of x squared minus 6x plus 5. And what's really cool about this is that now we're able to cancel x minus 1 and x minus 1. And then again, I'm going to rewrite it. And again, notice the limit as x approaches 1. And so since I'm able to simplify this, I get x minus 5. And then I go back to our good old friend substitution. We plug in 1 to our function, and we get this is going to be equal to -4. Okay? So this limit right here is -4. So basically there's a hole, right? If you guys remember graphing rational functions back in Algebra 2 and pre-calc, there's a hole right here at x equals 1, and the hole is at 1, -4. But you don't need to know any of that. You just need to know what the value of the limit is. Okay? So I hope that makes sense to you, and let's go ahead and keep on with number 4. So for question number 4, this question is a piecewise function, and it's y equals x squared, where x is greater than or equal to 3, and then y is equal to 6x minus 5 when x is less than 3. We do not need to graph this, and we actually talked about this in the very first video, that when we're looking at piecewise functions with context to limits, then when when x is greater than or equal to, it doesn't matter about the equals. We don't care about that. We did an example of that in the first video. When x is greater than, that's all I care about, then we know that if it's greater than, this is a right-hand limit, right? Because if it's greater than 3, like if we're at a number line and this is 3, then anything greater than 3 is going to be coming to the right side of 3 as we're approaching it, right? Because remember, we're approaching 3. So as we're going 3 and it's greater than, it's from the right, and then when it's less than 3, then it's from the left, right? So we're approaching it from the left. So what we have to remember here is notation, notation, notation. So we still have to write out our limit notation, but in this case here, we have to do the limit as x approaches 3 from the right. We talked about this in the last lesson, which is equal to, and again, we put our function down here, and we're going to get this is equal to 9. And then we're going to, so this is our right-hand limit, right? The right-hand limit as x approaches 3 from the right of x squared is equal to 9. So this is our function. And then, if we want to do the left-hand limit, we do 6x minus 5. We go ahead and plug in 3 here, right? 3 here. We get 18. 18 minus 5 is 13. So again, continuing on from what we talked about in the previous video, the very first video, is that our left-hand limit of our function does not equal our right-hand limit. So hopefully you guys know from the first video that I can now say, well, what can I say about this overall limit? I can say that this overall limit, the limit as x approaches 3 of f of x, and again, notice the notation, does not exist, right? And basically, if this had been 9 and this had been 9, there's your answer. The limit is 9. But anything that's not matching here, the limit is going to not exist. All right? So this is, again, piecewise function. We talked about it. Right-hand limit when x is greater than the value. Left-hand limit when x is less than the value. Just a side note for a second, if I had changed this number, I'm always trying to think about what questions students ask me in class. If I said what happens if this limit had been x approaches 1, if x had been approaching 1 and that's it, then you would just simply look at what's right here, because 1 is less than 3. So you would do a substitution. So the limit as x approaches 1 would be just 6x minus 5, and that value would be 1. All right? So if it's not, this number matches these right here, then just figure out where it falls on the number line and then plug in. So pretty straightforward problem, I think, with that. Okay, so now we're going to go to question number 5, and notice that this is a one-sided limit. So we're only caring about the fact that the limit as x approaches 5 from the left. Why do we care about that? Because if this had limit as x approaches 5, just normal 5, then we would know that there would be an asymptote here, and then we know that it would not exist. But we can have a left-hand and right-hand limit exist with the overall limit not existing. So here's what you got to do, and this is kind of like the side note for this. So if we're looking at 5 from the left, right? So here's our number line 5, and we're approaching 5 from the left. We want something really, really, really close to 5. And so the number that's really close to 5 to the left, I'm going to do is 4.9. So this is my side work. So I'm not going to do the actual work here. So I'm going to go ahead and plug in 4.9 in for x. Because I know if I graph this function, ladies and gentlemen, I know that there's an asymptote at x equals 5. So since I know there's an asymptote at x equals 5, right, and we talked about this again in the first video, so all this comes back. So if there's an asymptote here at x equals 5, I know that my answer is either going to be positive infinity or negative infinity, because I'm approaching it from the left. So either the graph is going to be doing this, or it's going to be doing this. And I got to figure out which one it is. And I don't want to spend time graphing the problem, and I don't need to really do that, so try to do it like this. So again, I'm going to put 4.9 minus 5, and then we do 4.9 plus 1. And most students can do this in their heads. And all I'm looking for right now is I'm looking for signs. I'm looking for what the sign is going to be. So what do I mean by that? So if I take 4.9 and subtract 7, and essentially 5 too, right? But if I take this number at the top, I'm going to get a negative value, right? So the top, I'm going to get a negative value. If I look at 4.9 minus 5, I'm also going to get a negative value. If I take 4.9, excuse me, and then add 1, I'm going to get a positive value. So since I've got a negative over a negative times a positive, these are values, these are numbers. So I know that because of this, I know that I've got a negative on the top, a negative on the bottom, and so these are going to make these positive. So I know that this answer is going to be positive infinity. And yes, technically, we would say that it does not exist, but a better answer would be positive infinity. This is the answer that they would be expecting you guys to do on a multiple choice. If this, again, been for your response, I don't imagine where it ever would be, then yes, does not exist would be very easy, and you wouldn't have to even worry about doing all this work because you know there's an asymptote at x equals 5. Okay? So you just want to be very careful with that problem, and if this had not been factored out, plug in first. If you plugged in and you get a number over a number, then that's the value. You don't have to worry about, trying to simplify stuff down. All right, so hopefully that makes sense to you, and let's keep on moving to the next part. Okay, so the next part we're going to talk about is other strategies. So we talked about substitution, and we talked about factoring. So now we're going to talk about other algebra manipulation problems. I will tell you guys there's something called L'Hopital's rule, which we're going to learn in this unit. It's like lesson 5 or 7, something like that. But so you can actually apply that as well. But the reason why we do these examples for you now is just to make sure that your algebra skills are really good for what we do later in the course, because you need some really good algebra skills. So the limit as x approaches 1. And by the way, so let me just actually say something really fast. If you plug in 1 to the top, you're going to get 1 over 1, which is 1. And then you can plug in 1 here, you're going to get 0, right? So you get 0 on the top. And then if you plug in 1 on the bottom, you're going to get the same thing. You're going to get 1 minus 1, which is 0. So we have to realize, okay, this is another way of manipulating our problem. We want to be able to cancel something out. So we tried factoring. Clearly factoring doesn't work here. So what we're going to do is we're going to combine our fractions. We're going to get a common denominator. And so in the very top, we're going to get 1 over x minus x. So how we are going to combine our fractions, and I'll give you guys a nice little easy function here in a second. I'll show you guys how I'm doing this, like how I'm able to get this pretty quickly in my head. So if I were to actually combine this 1 minus x over x into a common denominator, then I'm going to get 1 minus x squared over x. And really all I did is this. And I'm not trying to insult anyone's intelligence when I do this, but it's always nice to review for students just basic algebra stuff because we're so conditioned to calculators, and we have stopped using them pretty much in pre-calculus and definitely in this class here. So if I'm trying to add or subtract two fractions with denominators that are not the same thing, then all I do is I multiply a times d. And that's what I did right here. So this is over 1. So I just did 1 times 1, which is 1. I keep the sign. So whatever the sign is that I'm given. And then I multiply b times c. Okay. So over here, I just did x times x, which is x squared. And then I multiplied b times d. Right? These two things. So again, x times 1 is x. So you can actually probably do this one very easily as well, right? So it's going to be 1 minus x all over x. And again, ladies and gentlemen, remember that we are keeping the limit notation here. We need the limit notation. It's really, really, really important for us to continue on. Now, this one actually ends up being pretty sweet for us because the denominator in the top is also equal to the denominator in the bottom. So we can actually just cancel these two things out. If that had not happened, so again, little side note for this, if I had two fractions and the b and the d are not equal to each other where I can simply just cancel them out, then, and this is basic algebra 2, right? Maybe even algebra 1 when you learn this. But when you're dividing by a fraction, then you really multiply by its reciprocal. And that's the easy way to get that back. But we don't have to worry about that in this example because the denominator is actually the same. So that's actually pretty awesome for us. So we're left with this. And then we try substitution again. You always want to try substitution. Again, when you plug in 1 to the top, you're going to get 0. In the bottom, you're going to get 0. So we have to do one more thing. And in this particular example, ladies and gentlemen, it should be pretty obvious what we need to do. Now we're going back to factoring, right? So we're going to do 1 minus x, 1 plus x. There's a difference of 2 squares on the top, and then 1 minus x on the bottom. And so we're able to cancel out. One of my students asked me, okay, what happens if this had been 1x minus 1? You can pull out a negative. So that happens quite a lot in calculus, that if this doesn't exactly match, the signs are different, then you just pull out a negative. And I know for calculus students, that's pretty common sense, but in my videos, I want to cover every basis of what students ask me or they want to ask me. They just don't want to be embarrassed by it. So I'm trying to, cover all my bases here in these videos. And so now we've done common denominators, we've done factoring, and now we have this really nice function. And that's crazy that these functions are the same. And so we're going to do substitution. So now we've done all 3 of them, and I get that this limit here is actually equal to 2. All right, so hopefully that makes sense. And we're going to go and do one more example, and then we're going to end this video. So hopefully you have the energy to watch one more problem. We're good to go. Okay, ladies and gentlemen, now we're in example number 7. And in 7, we're doing the limit as x approaches 0 of this crazy function with radicals in it. And just like before, I'm going to try to save a little bit more time here. If you plug in 0 to the top and to the bottom, you're going to get 0 over 0. So in this particular example, we need to do our conjugate. So you don't have to rationalize your denominator in calculus. I will be saying this a lot throughout this course. You actually don't even have to simplify on the AB exam, or the BC exam, or the AB exam if you're taking AB. But you're taught how to do the conjugate because of examples like this. Why do we rationalize stuff? So I'm just multiplying by the conjugate. So this is the conjugate problem, right? So the conjugate problem. So hopefully you understand why I did this. This is just 1, right? This thing is 1. And so you change the sign, and students always mess this up. You just change the sign of what's right here. You don't change the sign of what's underneath the radical if there's more stuff to this. And so again, notice my limit right here, my notation, and I'm going to keep my notation for this. And notice that I do change colors a lot. And the reason that I do that is that if a student is asking me to look at an example, well, what was the purple step? That's supposed to be a really bad 0, by the way. So what's going on in the purple step? And so I can tell them what I'm doing. So I'm going to multiply the top, okay, the top together. You don't have to spend too much time thinking about this because this is a difference of 2 squares. Hopefully you guys can see this, or well, the factored out version of that. So if I FOIL this together, I'm going to get the top is going to be 2 plus x. And then this term here, the O and the I are going to cancel out, and you're going to be left with this should be a square root of 2. There we go. There we go. So 2. And then I always tell students, never distribute this. It's always going to work out. You don't just put whatever this is, multiply it by that. You just leave it alone. Do not. So I'm telling students, if you have a radical and a non-radical term, so there's no radical in this one, just leave it alone. And then when you look at the simplified version of this, and I'm going to try to go a little bit faster with this one. So you're going to see that there's an x on the top, right? There's an x on the bottom, and this is why, again, 2 minus 2 is 0, so we're just left with the x. And this is why this is perfect, because usually, again, 99% of the time, whatever is up here is going to be whatever this term was at the bottom right here. So whatever this little guy was right here. So they're going to cancel these little 2 things out, and we're going to write one more time the limit as x approaches 0 of 1 over the square root of 2 plus x plus 2. And we already know that this cannot be 0 over 0, so all we have to now do is substitution, and we're going to be left with 1 over the square root of 2 plus 2. And I feel like I keep dropping. Why do I keep dropping the square roots? I'm glad I'm doing this now. So it's going to be 1 over the square root of 2 plus the square root of 2, which is going to be 1 over 2 square roots of 2. Okay? And that's totally fine for us. You can rationalize the denominator if you want to. So I'm so sorry that I keep dropping these square roots of 2, but this is the right answer. Okay? So hopefully that makes sense to you guys, and we're going to come back and do the third video for the first lesson. But I hope this makes sense. So this is all limits solved algebraically and the techniques that we've done. So I will see you guys back in the next video.